So welcome to Math 349. This is lecture maybe 11, I'm not sure. I'll double check later. And so what I want to do is I want to continue talking about some of the material for the Fibonacci book project. So in the last class, we talked about Zeckendorf's theorem, that if we define the Fibonacci numbers as 1, 2, 3, and so on and so on and so on, then every number can be written uniquely as a sum of Fibonacci numbers. And it turns out that this is an equivalent definition of the Fibonacci numbers. They are the unique sequence such that every integer can be written as a sum of non-adjacent terms. How many people have experience expressing numbers as the sums of Fibonacci's? This is something you do. So you actually go and you write down numbers as sums of Fibonacci's, and this is how you add with things. Okay, so we've got one person. I actually have done it sometimes when I'm talking with Europeans or Canadians. Did we talk about that application last time? Okay. So for instance, here is, Zeckendorf's theorem. So here's the number 2012. And we talked about how you can write it as a sum of non-adjacent Fibonacci numbers. Does anybody know approximately how you convert from miles to kilometers or kilometers to miles? Yeah, which is approximately the golden mean. And as your numbers get larger and larger and larger, each Fibonacci number is approximately the golden mean times the previous. So if I wanted to convert 2012 to kilometers from miles, I would just shift all the indices by 1. If I wanted to convert from kilometers to miles, I would shift all the indices down by 1. And that is actually amazingly close. It's a horrible way to convert from miles to kilometers, but it is a interesting tidbit over here. How do you normally write numbers? We normally don't write numbers as sums of Fibonacci's. How do you normally write numbers? As integers, well, how? How do you represent the number? Base 10. Why do you use base 10? Raise your hands if you know. Raise your hands if you know. We have 10 fingers, right? Do you think the universe cares that we have 10 fingers? No. Above my pay grade to prove that. You can go to the philosophy wing of Williams if you want to talk about questions like that. There doesn't seem to be anything special about 10. What other bases might be a good base to use? 2. What else? 3? 3 actually beats base 2 for disk storage. It's more efficient for that. What other base? Not so good for integers, but good for calculus. E. And in fact, the reason that 3 is sometimes better than base 2 is that E is closer to 3 than it is to 2. This is another base to use, another expansion to use for numbers. Once we start doing this with the Fibonacci's, you could ask, of course, can we do this for other recurrence relations? How much is special just because it's the Fibonacci's? And one of the big things we did when we had the cookie theorem was at the end of the day, we had this beautiful explicit formula for how many ways there were to write, or how many integers between the nth and n plus first Fibonacci number had exactly case summons in their Zeckendorf decomposition. We know the largest summand has to be Fn. It can't be Fn minus 1. And a lot of these things you should try to prove. Show that if you don't have Fn, there's no way you can live between Fn and Fn plus 1 if you can't have 2 adjacent terms, that you would just be a little bit too small. This is beautiful when you have something like this, when you have a nice closed explicit formula that you can work with. This is a binomial coefficient. There's a lot that we can do with something like that. Unfortunately, in the general case, we do not have anything as clean as this. It's also worth remarking here that we have something with 2 indices. So everybody has seen sequences with 1 index. If for no other reason than when you've seen Riemann sums, and maybe a sub n is f of, or maybe a sub k is f of k over n, and we're dividing the intervals 0, 1 up into n equal spots, evaluating the function, calculating the upper sums and the lower sums, and doing everything like that. The theory of sequences when you have 2 indices or more becomes a little bit more complicated. There's a lot of wonderful things we can do with the Fibonacci numbers that become a little bit harder to do when you have more indices. But there are still things you can do. sometimes you lose the ability of getting a nice closed form expression. And so I taught a class on baseball, or actually sports mathematics, last year, and just finished a paper with some students. It's nice when you have a closed form expression, because if you then change something, you can immediately see the impact. Trying to think of what examples I can choose. Have people seen the spring law? The force is proportional to how much you stretch the spring. And does anybody know what else it's proportional to? The spring constant. So if I change the spring constant, because I have this nice explicit formula, I know immediately how the force is going to change. When you don't have anything nice and explicit like this, you're forced to do numerical techniques. And then if you change parameters, you then have to do the calculation again. That's expensive. If you have closed form expressions, if you have many different parameters at your disposal, you can say, well, what happens if I change this parameter? What happens if I change that one? And you can get a sense of, very easily at times, which one should you be changing? So if people do pursue this, there's a lot of stuff we can do with sequences that have multiple indices and trying to get closed form expressions. Okay, we talked very briefly about the fact that the number of summons is a Gaussian. This is one of the most famous distributions in probability. If you've done, has anybody done any advanced probability here? Advanced statistics? Okay. So this shows up all the time, that if you look at a bunch of independent, identically distributed random variables, and you calculate the sample mean. So for each observation, I record what value do I get, and I add a bunch of them together. Then one would hope that the average of your sample would converge to the average of the population. And it turns out it is true. And you would hope that it's going to get tighter and tighter and tighter, that the more observations you take, the better job it should do approximating the population's true mean, the closer it should be. And the central limit theorem tells you not only is that happening, but that the distribution about the true mean follows a Gaussian distribution. And so this is one of the most natural things to conjecture in terms of behavior. So many things in life are normally distributed. And there is, not just a normality here, but we actually have complete understanding of which normal it should be. So what do you need to specify a normal distribution? The mean and the standard deviation. So in some sense, I can always adjust things to have mean 0. If the mean is 15, just subtract 15 from every value. If the standard deviation is 3, I just divide every value by 3, and I've now decreased the standard deviation by a factor of 3. So to some extent, I can always adjust my distribution, if it's normal, to be the normal with mean 0 and variance 1. I will risk asking the following. I'm not expecting anybody to remember these. How many of you at least know that there's this thing called log laws? The log of a product is the sum of the logs. The log of a difference is the quotient of the logs. The log of a power is the power times the log. The log of the reciprocal is the negative of the log. And there is a final log law, the most forgotten. Anybody know what the final log law is? I'm sorry? Not the log of the log. The change of base formula. The log of x base b is the log of x base c divided by the log of b base c. And the reason this is such an important log law is that it means you only have to understand logarithms in one base. Once you know logarithms in one base, you can get any other base by just doing a division. Does anybody have a guess as to which is the best base to use for logarithms? E. And the reason is we have nice series expansions for logarithms in base E. And so everything becomes very nice and clean. So you only have to study one base. Once we know logarithms in one base, we're done. In the old days, they used to have tables of logarithms. Why would they have tables of logarithms in different bases? Yeah, but I mean, you only need it in one base. Not a bad, but no, not to torture students. Why wouldn't we just provide one base? Why would we have logarithms in several bases? Right. Right. I mean, it's convenience. If you're doing something numerous times, it's worth taking the time and just creating, let me have logarithms base 10, logarithms base e, maybe logarithms base 2. I don't know how popular 2 was before computers. And of course, once you have computers, at least once you get good, fast computers, this can all be done easily internally. They all have this just stored and they don't have to display it. But a lot of it is convenience. How many of you have ever looked at sports standings? People see that they list how many wins a team has, correct? And how many losses a team has. And then they list the winning percentage. Do we need to list the winning percentage? No. Do you want to trust Americans to do division? No. And you don't even want to do division if you had to, right? So a lot of times it's for convenience. And so the change of base formula is wonderful. It allows us to pass knowledge from one base to any other base. But for some purposes, it's actually not a bad idea to have a couple of things written out explicitly. In the old days, we used to have tables of integrals, and they would list a lot of integrals that were equivalent separately, just because that way when people are looking for things, it's easy to see it that way. So over here, when we're talking about a converges to a Gaussian, we always want to be specific if we can, which Gaussian is it converging to? And we can figure out what the mean is and what the standard deviation is. And then I talked a little bit about the proof. And the proof in principle is very straightforward. Is we have an explicit formula for how many integers in the interval have exactly k summing k plus 1 or whatever. One of the things you always have to be careful about is what is the best way to do the algebra? And so sometimes one algebra approach is a little bit easier than another. And so you might want to shift things. And then rather than looking from Fn to Fn plus 1, it might be easier to look from Fn plus 1 to Fn plus 2 or something like that. It's not a big deal. It's just I initially had a k minus 1, and this is where I get rid of the k minus 1. Whenever possible, I want to clean things up. Has anyone here taken real analysis? Okay, so in real analysis, have you seen 3 epsilon proofs? You break something up into 3 parts and you show each part is less than epsilon, so the sum of the 3 things is less than 3 epsilon. If you want to, I think look cool is a bit strong, but if you want to look like a professional mathematician, you arrange each one not to be less than epsilon, but to be less than what? I'm sorry? Not delta. So if you have each one less than epsilon, then the sum of the 3 is less than 3 epsilon. Yeah, you arrange each one to be less than 1/3 epsilon, because then that way at the end of the day, you've shown it's less than an arbitrarily small amount epsilon, rather than showing that it's less than an arbitrarily small amount 3 epsilon. It's not really a big deal. But just sometimes in terms of how you present the algebra is just a little bit cleaner if I shift things and have a k rather than a k minus 1. And then we just use Stirling's formula. And so Stirling's formula is wonderful. It allows you to approximate n factorial or k factorial if n and k are large. Now you've always got to be careful in terms of what is the error. If I'm trying to estimate how much money you have in the bank, and I'm off by $1 million, if that is not a significant error, please see me after class. Or send me a text right now and I will adjourn class right now and we'll talk. Okay. Most of us, $1 million error would be significant. For Elon Musk, would $1 million net worth be significant? Not at all. And so whenever you're looking at errors, you always have to remember it's relative. So when we're trying to get an estimate of how big is n factorial, when we look at our approximation, how close are we? If you're off by a factor of 100, is that a lot? I would say being off by a factor of 100 is a lot, but if you have a huge number, if your number's of size, 10 to the billion, okay, and it's really 10 to the billion and 2, yes, I'm off by a factor of 100, but I'm pretty damn close. And so we often look at not the number, but the logarithm of the number. So if I take the log of 10 to the billion, what base should I use if I'm talking like this? 10. So let's say I take the log of 10 to the billion base 10, what do I get? A billion. And if I take the log of 10 to the billion and 2 base 10, what do I get? Basically still a billion. The error is so small, right? You'd actually get a billion and 2. So you'd be off by 2 over a billion on a log scale. That's insignificant. We're not going to see something like that. So whenever you have expressions like this, and we're going to try to feed in Stirling's formula, we're going to be estimating things, and we want to see how accurately are we estimating things. Frequently, we convert to logarithms. And every now and then, in your undergraduate career, you come across something that's worth remembering. Most of the time, the content we give you, you should forget. Any Sherlock Holmes fans here? Okay, so do you know his philosophy about his mind and storage? So I think the very first time Watson meets Holmes, Watson is shocked when I think he says something like, wait, the moon goes around the Earth, not the other way around? Okay, well, I'm going to try to forget this as quickly as possible. I believe my mind can only store so many things, and I don't want to fill it with useless clutter. The Earth-Moon motion, that has nothing to do with anything I do in my life. What do? So which things do you want to remember? Most of the things you learn, this is the 21st century. You can quickly go online and search it. You want to understand, how do you approach things? How do you look at things? And when we're writing books, this is what we really want to emphasize. This is why I'm babbling like this and not throwing tremendous amounts of information at you. You can read stuff later. You're all smart people. You're at Williams. This is a 300 level course. I trust you to be able to read math papers. I want to talk about the philosophy and what we want to emphasize. And so when we're writing this up, we really want to hammer home, how do you look at things? A lot of times when you have nonlinear relationships, if you do a log or a log-log transform, you either take the log of just the x-axis data, the y-axis data, or the log of both, all of a sudden things become a straight line. This was the main idea of calculus, or at least of differentiation, that locally any differentiable function looks like a straight line. I understand how a straight line works. And so we approximate complicated functions locally with straight lines. If you want something better than a straight line, what would you use? So what would you do instead of a straight line? What's the next simplest shape we could try? Not a circle. I'm sorry? What curved line? What would come after a straight line? Next, we had a parabola. And if the parabola doesn't do a good enough job, what would you try next? A cubic. As you keep adding more and more terms, this is how you get Taylor series. You try to approximate your function. If a line is not doing enough, you approximate it with a parabola, then a cubic, and so on and so on and so on. Whenever you see a product of items, you should always think about taking logarithms. And the reason is the log of a product is the sum of the logs. We do not know how to do multiplication. We're just not trained to do multiplication. We do everything in terms of addition. We do Riemann sums, we do stuff like this. We've done sequences, we've done a lot of results about when these converge and whatnot. There's really no difference between sums and products. If I give you a product, if I take the logarithm, there's now an associated sequence of sums where each sum is just the log of the corresponding piece in the product. Conversely, if I give you a sum, if I exponentiate it, the exponential of a sum is the product of the exponentials. You can go back and forth, but it's just more convenient for us. We're just more used to looking at things as sums. So why not do a logarithmic transformation. And you see, very quickly, after I do some algebra, or my students do some algebra, we're trying to understand Sn, so we take the log of Sn and we start having lots of pieces. And then we want to start to expand things out. And so I don't want to go through all of the algebra. And so I just want to try to find like maybe like one or two good terms to look at. So let's see, we have like a n minus mu plus x sigma. We've got to be very careful in terms of what the size of things are. If we take these two logs and multiply them together, we get the log of n minus u plus the log of 1 minus x over sigma. I mean, x sigma divided by n minus u would become the log of the product. So when the n minus mu hits the 1, you get an n minus mu. And then when n minus mu hits n minus mu, that cancels, and you would just get x sigma. So this would be n minus mu minus x sigma. That's exactly this piece over here. I've just pulled out an n minus mu. And so if x times sigma is much smaller than n minus mu, then this is approximately the log of 1. What's the log of 1? 0. So it turns out the mean is about 0.276n. So the denominator here is about a multiple of n. Sigma is going to be of size square root of n. Okay, so this, as long as x is not too large, that term is going to be very, very small, and I can approximate this as it's essentially just the log of n minus mu plus something very, very small. And this is how you do analysis like this. You keep breaking things up into what's my main term, what's my lower order term, and you just do careful bookkeeping. And at the end of the day, you say, okay, I've got this thing over here, which is looking like a Gaussian, and I've got this small little pollution, this small little error. And as n gets larger and larger and larger, the error gets smaller and smaller and smaller. And this is how it converges to a Gaussian. If you really care, you might want to know more than just that it converges to a Gaussian. What else might you want to know? Well, okay, so which Gaussian would be knowing the mean and the standard deviation, which we know. Good. What else? How long will it take, right? Okay, so it's going to converge to a Gaussian. How many people have taken statistics? So when Moses came down from Mount Sinai, I think I might have said this before, yes? Okay, everybody knows about the 10 Commandments. And then there were a bunch of other additional addendums for mathematics, statistics, physics, and whatnot. And one of them is how large n must be for you to use the central limit theorem in statistics. Anybody remember this? If n is about this, they can't really yell at you if you say, yeah, it's a Gaussian. Anybody remember? Around 30. So if n equals 30, people usually just say, okay, we can just approximate it by a Gaussian. And so for many nice distributions, the convergence is not taking too long to hit. There are some things that I'm looking at where billions of data points is not enough yet to see the limiting behavior. The convergence is extremely slow. And so you always want to get a sense of how quickly do you have to wait before things kick in. And when you do this analysis, not only do you get the main term, but you get a lower order term. And that lower order term will tell you how quickly the Gaussianity is setting in. And so I'm not going to go through the rest of the algebra. There's a lot of it. And eventually it ends. What I want to do now, and this will be new material for today, is frequently in life, we look at the wrong problem. We start off with something that we're interested in, but as a general rule, you should ask, well, what is an easier thing I can look at and build intuition? There is a danger with this. Sometimes if you look at a problem that's too simple, you might have very specific methods that work just for that problem that don't generalize. But it's not bad to try to think, what can we look at? And so the Fibonacci's is a sequence. It's defined by recursion. Well, what if I consider other recursions? So here we'll let hn plus 1 be some combination, c1 hn all the way down to cl hn minus l plus 1. And it's frequently useful if the coefficients are non-negative integers. It turns out that the first coefficient should definitely be greater than 0. It should be at least 1, or things become much more complicated. The last coefficient clearly has to be greater than 1. Otherwise, what? If the last coefficient was 0, would I write it? No. So because I'm writing it like this, the last coefficient shouldn't be 0. And so we showed that every positive integer can be written uniquely as a sum of non-adjacent terms if the h's are the Fibonacci numbers. And we talked about how we can calculate the average number of summons and we can prove a Gaussian behavior. This holds in much greater generality. Now, the algebra becomes a lot worse. And so, you have roots of more involved polynomials of 2 variables, but we still have expressions that will tell us what is the mean. So for the Fibonacci's, it was approximately 0.276 n was how many summons you had on average. Here it's c times n, where c is given by the monster expression here. And this is where it's really nice to work with lots of smart undergraduates. They can calculate all this stuff. So this was all done by students at Williams. And then we still have a central limit there, that as the number n we look at gets larger and larger and larger, and we want to look at a integer between hn and hn plus 1, and we want to look at this generalization of a legal decomposition. So for the Fibonacci's, a legal decomposition was we couldn't take 2 adjacent summons. Essentially, the notion of legal here is if we have the recurrence relation, we shouldn't be able to use that to replace some summons with another one. And if you think about what's going on with the Fibonacci's, if we have 2 adjacent Fibonacci's, we can use the recurrence relation to replace it with the next one. Essentially, that's what's going on here. We shouldn't have something where we can just quickly replace. Gaussianity still holds. Now, what I want to do is I want to try to motivate this by looking at an easier problem. So rather than looking at the Fibonacci numbers, let's look at something simpler. Instead of looking at a recurrence relation of depth 2, let's look at a recurrence relation of depth 1. And since most of us, not all of us, have experience in writing things in decimal, let's look at the decimal expansion. So I'm going to let hn plus 1 be 10 times hn. And I'll take my first value, h1, to be 1. And then you can quickly see that hn is just 10 to the n minus 1. And so a legal decomposition is just going to be writing my number in decimal notation. Okay? So now what I want to do is I want to calculate how many summons does a typical element have between hn and hn plus 1. We have to be a little bit careful. All of the possible a's, they can be any integer from 0 to 9, except for the leading term. If we're between hn and hn plus 1, then the first term has to either be a 1, a 2, a 3, up to a 9. So there's a slight restriction on the first term, but other than that, everything is from 0 to 9. Okay, so if I think about what's going on, I can choose any value of a from 1 to 9 for the first, and any value of a from 0 to 9 for everything else. And that will give me a number between hn and hn plus 1. And conversely, every number between hn and hn plus 1 has a unique decimal representation. As a nice exercise, prove that you can't write a number in base 10 2 different ways. Okay, so you should be able to prove that. So now I want to just count how many ways do we have. So can somebody tell me how many ways, and you can be off by a factor of 10, do we have of writing numbers between hn and hn plus 1? How many numbers do we have in that interval? I'm sorry? Well, no, I'm looking from hn to hn plus 1. How many integers lie between, say, 10 to the 5th and 10 to the 6th? So from 10 to the 5th to 10 to the 6th, how many numbers do I have? I'll do a smaller one, 100 to 1,000. How many numbers are there from 100 to 1,000? I'm sorry? 900, right? How many numbers are there from 100? I'm sorry, from 100,000 to a million? 900,000. So how many numbers would they be from 10 to the 5th to 10 to the 6th? 9 million. I'll assume you've done the algebra correctly. I don't want to risk doing that in public. So basically, you have 9 choices for the first digit, and then 10 choices for everything else. So just, like 9 times 10 to the n minus 1 or something like that. So we know how many integers there are very easily. It's just, hn plus 1 minus hn. And it's just going to be 9 times, 10 to like n minus 1, something like that. Okay, now we want to calculate the distribution of the number of summons. So if we want to, how many numbers have exactly 1 summoned? How many have exactly 2? Well, if you want to have 1 summoned, you've got to be the number, 1 times hn. If you want to have 2 summons, what could you be? So which numbers could have 2 summons? I'm sorry? 3hn? 3hn would have 3 summons. 2hn would have 2 summons. What else would work? So let's go from 100 to 1,000. Give me all numbers from 100 to 1,000 that have just 2 summons. There's 100 is the only one that has just 1 summon. Which numbers would have 2 summons? Does everybody see why 100 has just 1 summoned? It's 1 times 10 squared plus 0 times 10 plus 0 times 1. 100 has just 1 summoned. 300, how many summons would 300 have? 3. 200 would have 2 summons, 2 times 10 squared plus 0 times 10 plus 0 times 1. So what other numbers would have just 2 summons? 110. What else? Anything else? There's one other number that has just 2 summons. 101, right? Not 102. How many summons would 102 have? 3. So the numbers that have just 1 summon is 100. 2 summons is 200, 101, and 110. What about 3 summons? Okay, so the question is, what's the way to methodically go through this so we don't miss anything? Which do you want to do first? So you could start down and go up. I like to start up and go down. Here, let me look at the leading digit. I could have a 3 there. I can't have a 4 or higher. So I could have 300. And that's the only way to do it with the leading digit of a 3. Then I could have a 2. And what are all the ways with a 2? 210, 201. Then I could have a 1. So if I have a 1, what could I have? 120, 111, 102. And that's a good methodical way to go through this. Okay, so we could keep doing this. We could keep listing all the ways. And then the question is there a nice closed form expression for how many numbers have exactly k summons? You know that the first digit can't be a 0. It has to be at least a 1. So as a nice exercise, try to see if you can come up with a nice closed form expression for how many numbers have exactly k summons. This might be a situation where we might be looking at the wrong thing. Maybe it would be more convenient not to look at the numbers from hn to hn plus 1, but to look at the numbers from 0 to hn plus 1. Because then I don't have to worry about that first digit being a little bit different. So one way to prove that things become Gaussian is to appeal to the central limit theorem. I can choose any number for my second digit from 0 to 9. I can choose any number for my third digit from 0 to 9. These are all independent variables. So in probability, we usually use capital letters to denote the random variable and lowercase letters to denote the value that they take on. And so the central limit theorem says if you have a sum of independent, identically distributed random variables, and again, if you do this project, and if you haven't seen probability, I will talk to you at much greater length about this. Right now, I'm just trying to give you a sense of what's out there. One of the reasons I love this is a springboard to seeing some good math that you should have seen or should be seeing in the near future in a future class. And if you haven't seen it, I'm happy to go into more detail. So A2 plus A3 dot, 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 plus AN, this is a sum of independent, identically distributed random variables. It's going to converge to a Gaussian. And we know each one of them on average, we can calculate their mean and their variance. What have I ignored in the sum? Yeah, I've ignored A0, A1, A2. Okay. Is there anybody whose life would be fundamentally changed if I gave them a penny? Okay, I would have done it, but okay. It's too late now. So for most of us, you refer to that a penny is not going to really change anything, right? If I add just one extra term, you should think of n as going to infinity. Think of n as a googolplex. N is tremendous. And so the mean is going to be 4.5 n. All right, if I forget A1, at most I'd be adding another 9. I'd add at least a 1. That's insignificant next to the 4.5. So the fact that I've dropped the first term is not going to really affect the limits at all. And it just makes things cleaner because now all of my random variables are the same. Okay. Can anybody figure out why I keep looking at my watch today? Yeah, the clock is not working. Yeah, it is clearly not working, given that it seems to be saying it's a little bit before 6 a.m. Or it could be a little bit before 6 p.m. I guess we can't really tell. Broken, well, usually, if the clock is not moving, then yes. But if the clock is moving at a different rate, then you could have issues. But for the most part, yes. Okay, there's a lot of other things you can look at. So we looked at writing things as sums of Fibonacci numbers. For a lot of things, it's sometimes easier not to look at sums, but to look at signed expressions where you can have plus and minus. There's some really great riddles where you're trying to weigh something and you have one of these equal arm balances. Does anybody remember these from maybe high school or something? And the question is, what's the fewest weights you need to be able to determine how much something weighs? And it actually, I believe, is better to, I want to say it's base 3 to use. I'm not positive. I would have to think about this, where it matters which side you put it on. And you can, sometimes you put the object you want and some of the weights on one side, and then you put the other weights on the other side. And this gives you the advantage of essentially doing a signed decomposition. So for some things, it's convenient to be able to have plus or minus. And so it turns out you could write every number as a sum or difference of Fibonacci numbers with the following rule. Whenever you have two terms next to each other, if they're both positive or they're both negative, then the signs have to differ by at least 4. And if they are opposite sign, then they have to differ by at least 3. So in this decomposition of 1900, we have F17 minus F14 minus F10 plus F6 plus F2. The F17 and F14 have different signs in front of them. They differ by 3. F14 and F10 have the same sign. They differ by 4. And so this is an interesting theorem. You can ask, of course, does this generalize? And then you can ask, well, what about on average, how many summons do you have? And now, when you ask about how many summons you have, there's a couple of ways you could answer this. You could ask about how many positive summons do you have, how many negative summons do you have, and how many summons do you have total? Or maybe the difference between positive and negative summons. Well, if you know how many positive summons and how many negative summons you have, you should be able to figure out a lot of other things. And so you can ask, are there central limit type theorem? And there are. And what's interesting is it now converges to a bivariate Gaussian. So it's going to have 2 variables. In terms of the positive and the negative summons, there's going to be correlations. And so the number of positive summons and the number of negative summons are not independent. Okay. So I don't think we've proven Binet's formula yet in this class. Is that correct? Okay. So this is one of my favorite formulas in all of mathematics. I think we might have talked a little bit about this. I had a student who thought about doing this because I said I'd give them an A+ in Math 150 if they calculated, I think I said the trillionth Fibonacci number by hand. And just, I'm sorry? No, it was a few years ago. And just, you can estimate just how many additions would you have to do because the Fibonacci numbers are growing exponentially. And you might get to the point where there's not enough atoms in the universe to physically write down what you would have to do. So the Fibonacci sequence, in principle, it's very easy to work with because once I tell you the first two Fibonacci numbers and the recurrence relation, I know everything else. In fact, I don't even have to tell you the first two. I just have to tell you any two Fibonacci numbers. And because I know the recurrence relation, I can figure out everything. It turns out that there is a closed form expression, Binet's formula, that allows you to immediately jump to any Fibonacci number. When you look at this expansion for the nth Fibonacci number, does this look like an integer? No. We've got divisions by 2. We've got square roots of 5. Amazingly, everything cancels. So there's a lot of ways to prove this. One of my favorite proofs, which I'm not going to do, is the method of divine inspiration. And what you do is you just take that as your guess for Fn, you show it satisfies the recurrence relation, you show that when you take n equals 1, it's 1, when n equals 2, it's 1, therefore this must be the Fibonacci's. So if you're divinely inspired and you believe that this happens to be Fn, you can just write that down and show that it works. What's the problem with divine inspiration? You have to start with the answer. And so, I mean, there are definitely a lot of prayers on exams, asking for divine inspiration, but there's a lot of things that the divinity has to do and is not always available to, help you in your time of need. So relying on divine inspiration is not an optimal strategy for mathematics. So if we can come up with a way to attack slews of problems like this, that's great. And so what we do is we do what's called a generating function. And at first, it looks absurd. I'm going to define g of x to be a sum of fn times x to the n. Well, the whole point is I'm trying to figure out what the fn's are. But in some sense, once I give you the recurrence in the first two values, I do know what all the fn's are. I just have to find a way to extract the knowledge that I have. And so what we're going to do is we're going to play a lot of algebra games. Has anybody here taken differential equations? Okay, you might have seen this in doing sequence solutions or series solutions to differential equations. It's the same idea. So let's look at the sum fn plus 1 times xn plus 1, and I'm going to have n go from 2 to infinity. Well, by the recurrence relation, fn plus 1 is just fn plus fn minus 1. So notice all of these functions are very similar to g of x. G of x starts with n equals 1. This is starting essentially with n equals 2, but it's really n plus 1, so it's really like starting with n equals 3 in g of x. So it's really just g of x minus its first two terms. When you look at the next one, fn x to the n plus 1, boy, does that look close to g. What should I do to fn x to the n plus 1? Divide by x, or just pull out the x. And for the next one, I would pull out an x squared. And so I first just shifted the index of summations a little bit, and then I pulled out the x's as was mentioned, and I get fn x to the n equals x, fn x to the n plus x squared fn x to the n with the appropriate ranges of summation. Well, these are almost g of x. I just have to put in the extra terms. You can't just add in terms, but you can add them and subtract them. And so if I just subtract those extra terms and add them in, the left-hand side becomes g of x minus f1x minus f2x squared, and similarly on the right-hand side. I now have an equation for g of x, and I can solve. And when I solve, I get g of x is equal to x divided by 1 minus x squared. And we now have a formula for g of x. Well, g of x is defined as the sum of fn x to the n. So the hope is we can somehow pass from this to expressions for the fn's. And so we have our generating function. You might try to expand x over 1 minus x squared as a geometric series, where the denominator is 1 minus r, where r is x plus x squared. Try doing that and then just see how painful it is, because x and x squared have different degrees, so when you expand it out, it becomes a mess. I might have mentioned before that if you ask 100 students what is your least favorite integration technique, the ones who remember partial fractions always say partial fractions. The ones who are so traumatized they forget about it will immediately correct their answer once you remind them that partial fractions exist. Yeah. This is the technique students hate the most. Here's a place where it's useful. So I do a partial fraction expansion. I factored the denominator, and now I split up like this. Now I can do a geometric series expansion, because now I have something that from 1 minus r. And when I expand this out, I'm going to get powers and powers of x, powers and powers of x. And when the dust settles, you get Benet's formula. So it just comes from using the geometric series. It comes from the fact that we have this generating function. And now I can jump to any Fibonacci number I want. So this gives you, a sense of the power and some of the things you'll be seeing in the Fibonacci stuff. All right, so this is a good place to stop. We will continue with this on Wednesday.